One thing we're hoping to do here is highlight the differences in scale, and scale is a pretty important question considering permafrost carbon and its impacts both locally and regionally to ecosystems and globally. So my presentation is entirely complementary, and it's a regional scale examination of Thermokarst terrain suitability. So I've chosen the word suitability kind of for a specific reason here. It's sort of analogous to habitat suitability when you're talking about wildlife, in the sense that you may have a piece of landscape that's really good browse for, say, a moose, but that doesn't mean the moose is going to be there. And in similar fashion, terrain that is suitable for a particular type of hill slope thermokarst, it may be very suitable, but that doesn't mean there's going to be a feature there. It doesn't mean there's one there now, may not mean there will be one there anytime in the foreseeable future. So it's really kind of analogous to what David is talking about is sensitivity. So let's see, a couple of, for this crowd, we probably don't have to go over this too much. So for permafrost, a quarter of the global terrestrial surface is permafrost landscape. And with 1,700 petagrams of soil carbon, that's about twice the current atmospheric load of soil carbon. So permafrost carbon constitutes a significant pool. And when we're talking about permafrost degradation, CO2 is the thing that gets the most press, but you have to remember too that methane and nitrous oxide are also important, although much less in total volume. They're much higher in global warming potential, almost 300 times as much in the case of nitrous oxide. So all these things are part of, really part of the permafrost carbon feedback. So this is one of Joel Rowland's slides. I love this because you get like the entire permafrost apocalypse all condensed into one slide. But when you look at it, you can think about the trajectory of permafrost carbon once it's released. It depends a lot on landscape characteristics, where it's going to wind up going. So, for example, you might have released permafrost carbon being turbated and resequestered and not permafrost, but resolidified runouts of features that are hill slopes where they run into lakes and streams. They may wind up in the benthic sediments of the lake or stream, or they may wind up in the ocean. They may wind up being released by fire directly into the atmosphere, or maybe they wind up nutrient cycling their way down through the ecosystem before coming out in the stream. So there are a lot of different trajectories for carbon when it's released from permafrost, and they're related with the mode of permafrost degradation, which is one of the reasons for segregating permafrost degradation into different types. So for my study, what I'm looking at primarily or exclusively are two types of hill slope thermokarst. One is an active layer detachment, the other is a retrogressive foss lump, which are specific modes and include specific processes of permafrost degradation. So active layer detachment slides are very superficial features. They occur when the ice-rich transition zone, which is between the active layer and the upper permafrost, the permafrost table, simultaneously thaws and melts. And that instability causes the active layer to sort of en masse slide downhill. They can be fairly large. You can see the one on the left is the better part of 1 kilometer long and about 50 meters wide. They're more episodic. They tend to stabilize after a year or two. The next mode of permafrost degradation I'm looking at are retrogressive thaw slumps. And in contrast, these tend to be much larger and deeper. This one is almost 300 meters across and 200 meters from the head wall to the beginning of the runout. And these last a lot longer. They tend to go years to decades. In this photo, you can see in the middle of the feature there are some lines that are, they're sort of analogous to growth rings. They're not really annual in the way you would think with a tree, but you can see that they represent the progression of melting periods within the thaw slump. So for this study, the idea was to look at the locations of known and mapped features within the central and western Brooks Range in northern Alaska. So these are almost 3,000 active layer detachment sites and 800 thaw slump sites that were mapped beginning by me, and then I turned over my data set to Dave Swanson in the National Park Service, and he completed the carpet coverage mapping of this data set. So what we have are pretty rich data for actual physical locations of features. And the idea was to use these as the basis for empirical modeling to look at terrain suitability for these types of features. So in terms of timing, a lot of these have shown up in the recent past. There's a lot of emphasis right now on things changing quickly, and it's easy to pick places like this. This photograph is one of the old Alaska AHAP photos from the early 80s, and there's only one active layer detachment in this photo. It's represented by the green dot, and then this photo is from 2006, and you can see a lot of active layer detachments have shown up. It's hard to tell across the entire Arctic what the difference is in frequency of these features now versus at any time in the past. The idea is that there are increasing numbers of them, which may be true, but it's difficult to say whether or not it's just moving. This is the hotspot now, whereas 200 years ago it may have been somewhere farther south. So this study region fits in with what Tor and Yuri would call climate-driven ecosystem-modified permafrost. Places where the ecosystem, as it develops and you get an organic layer, the ecosystem itself modifies the cryostratigraphy in the permafrost itself, which in turn influences the type of permafrost degradation, i.e. these sorts of Thermokarst features that you can get. At the scale of a site, you can apply a conceptual model like this one, which is fairly complicated and is very process-oriented and very detailed, and includes both permafrost evolution and degradation. As you move up in scale toward a global look, similar to what David did, you begin to lose a lot of this detail because you simply don't have the data to populate this sort of thing. But what I did was try and get as close to this as I could, given a regional scale approach. So permafrost includes a vast diversity of landscapes, and those diverse properties, they form complex interactions, and they influence what type of Thermokarst feature you're likely to get in any particular location. So where in the study region might these features occur, and how much terrain is that? Well, the terrain suitability estimates I came up with were based on both categorical factors and continuous data factors. So, for example, we had things like lithology and superficial geology, which are divided up into categorical data and ecotype. And then we had things like derived topography, things like slope, elevation aspect from DEMs, and things like NDVI. So in order to accommodate that, there were two tracks of modeling analysis, and to accommodate both those things. So the idea is that we use these feature locations to extract the data from our spatial database and run the empirical analysis. So the first step was to deal with the categorical data, and this was done with integrated terrain unit analysis. Basically, the idea is that you extract the unit data from each data set, look at the proportions of features that fall within each specific land cover unit, and then come up with an estimate for how suitable that terrain is on that basis, and then scale it 0 to 100. So this map is kind of a quick look at what that looks like. Areas that are gray but brighter are higher terrain suitability, and areas that are darker are lower terrain suitability, and this is for active layer detachment features. So the next step is to use structural equation modeling, and this incorporates the continuous data. And this also produces a similar terrain suitability layer, scaled 0 to 100. But in this case, what you're doing is coming up with a hypothesis, basically, of how the processes link together and determine terrain suitability. And it's an iterative process where you populate this model, run it based on the empirical data, and then based on the model outputs, determine which factors are more relevant, drop some, add some, and rearrange them until you come up with a good model fit. So for the case of active layer detachments, this, after several hundred iterations, this is what the model produced. And the weight of the line shows you the relative impact of each terrain factor on the final output. And here's a map of what that looks like. Again, brighter colors are relatively high suitability and darker colors are relatively low suitability. And here is the final structural equation model for retrogressive thaw slumps. And you notice it is quite different than the one for active layer detachments. So the two features are responding to different factor interactions on the landscape. And these are important not just for these two different types of permafrost degradation, but across all a couple of dozen identified modes of permafrost degradation. So then the idea is to create a final terrain suitability map by combining them. So the idea is to multiply them together and then come up with a final map scaled 0 to 100, and you have one map for each type of feature, active layer detachments and thaw slumps. And here's what that looks like. So in this map, both active layer detachments and thaw slumps are represented on the same map. And thaw slumps are represented in red. So increasing intensity of red means a higher terrain suitability for retrogressive thaw slumps. And active layer detachments are represented in green. So the deeper the green, the higher the terrain suitability for active layer detachments. And because of additive primaries, if you see areas that are yellow, those are areas that are highly suitable for both active layer detachments and retrogressive thaw slumps. Another way to look at it, you can also define thresholds of suitability, and instead of a sliding scale, just look at how much terrain you actually have that you consider quote-unquote suitable. So the top green is the total suitable terrain for active layer detachments, and the bottom is for retrogressive thaw slumps in red. So let's see. Actually, for the sake of time, I think I'm going to skip this one, this talk. One key point that came out of this research is that including all the factors and interactions that are relevant, it tends to constrain the model. In other words, if you're trying to estimate how much terrain is suitable for any particular type of permafrost degradation, it's likely that the more interactions that are relevant that you include, you're going to constrain the estimate, and that failing to include relevant interactions and factors will lead to overestimation. So what you're seeing here, the bars on the left are how much suitable terrain there is within the study area for thaw slumps and active layer detachments. And then in the middle, the same for based on the structural equation modeling for both those feature types. So on the bars on the left and the bars in the middle, these are the individual structural equation modeling and integrated terrain unit analyses. When you combine them together, in other words, include all the factors that are driving terrain suitability, your final model winds up with significantly less overall suitable terrain estimated. So a quick look at what these kind of landscapes look like. The photograph on the right is an active layer detachment slide in an upland setting. It's fairly close to the number 1 on the map on the left, and it's right at the bottom of a toe slope where there's some barren rock coming into some colluvial deposits with a combination of wet sedge meadow and shrub tussock tundra. And as you grade down slope, if you're looking at the map on the left, as you grade down slope, you go from high suitability for active layer detachments, and then at about mid-hill slope, you start getting more yellow signature where it's suitable for both active layer detachments and thaw slumps. And the reason for this is that it's good active layer detachment terrain, but because it's farther down slope, there's also a deep enough deposit that once you have an active layer detachment expose the upper permafrost, a thaw slump can develop from it. And then as you move farther down slope toward the valley bottom, it tends to be much more just retrogressive thaw slump terrain. And for example, around the number 4, there are a lot of little kettle lakes in there, and a lot of that is derived from relic glacial ice, from glacial drift and till deposits. So in this slide, this is a different setting with much more retrogressive thaw slump terrain. And you can see some of the larger lakes, especially around number 2. Some of the biggest thaw slumps we looked at were there, and they were driven by a combination of large ice wedges, Pleistocene ice wedges, and late Pleistocene relic glacial ice. Relatively less active layer detachment slide suitability in this area, although some toward the hilltops. So This is combining soil organic carbon. This is from the Hugelius data set for permafrost carbon, and using the suitable terrain to kind of clip that and get a sense of how much carbon is vulnerable in this case. So this is kind of analogous to what David was showing is sensitivity. And on the top, you can see that active layer detachment slides tend to threaten less carbon overall than retrogressive thaw sumps, which are shown in the bottom, and or tend to be associated with landscapes having much higher soil carbon. So the final results were somewhat over half of the study region was deemed to be suitable terrain in the study. And the suitable terrain is highly diverse. There are some areas where a relatively low slope is okay, it's suitable terrain because ice content is so high. So if the ice thaws and melts, it causes enough instability that even at a low slope angle, it'll still fail. Conversely, you have some areas that are much higher slope, but they have lower ice content, but they're equally suitable. So factor interactions are driving this. From the standpoint of thinking about scaling, it's a nice fit with things that people are doing like David, looking at the global scale. The data that are available for this kind of a study are only available for limited places. I was lucky to have really good carpet coverage data sets for my study region to be able to do this. And those data just aren't going to exist for the rest of the Arctic at that resolution for quite some time. So fitting this together, you kind of think about it as sort of a nested study and having specific places where you can look and kind of drill down and get some of the specific processes involved on the landscape and get a better sense of globally what's happening and what's distributed out there. Another thing you might have noticed from David's slides are that a lot of what he is showing as high probability hill slope thermokarst terrain is in Eurasia. And it would be great to try this approach for some place in Eurasia and Siberia that has suitable data to do this sort of analysis. So that's pretty much the end of my talk. If there are any questions, I'm happy to take those now, or if not, we can have a more general discussion too. Okay, well, it sounds like there are no questions. Let's see. I saw something come up on the screen, someone trying to call in.
So Andrew, just a comment here, it's David. While you had your map up out of your study site, I brought up finally and had a side-by-side comparison to the product that I've produced and how it classified that area of Alaska. And I'm happy to say that in my map, it shows up as the highest possible coverage of hill slope thermokarst terrain.
Yeah, I noticed that too, actually. The one you have that zoomed, your zoom in of Alaska map shows that pretty nicely, actually.
Right, so we have two different approaches using different data sources, but at least they're corroborating each other.